Hi everyone, and firstly welcome to the virtual global conference on artificial intelligence and Internet of Things. My name is Leo Kong and I'm a postgraduate research assistant at the Smart Systems Group based at Harvard University, Edinburgh, Scotland. The following work is a partnership between the Offshore Robotics for Certification of SH Hub, Microsense Technologies Limited, and the Smart Systems Group. Today I'm delighted to be presenting Interactive Digital Twins Framework for SH Management through Internet. Here is a brief overview of this presentation. The general benefits of our digital twin framework for asset management is discussed. Next, the technical challenge which engineers face when developing a digital twin framework is presented. Then I outline the solution to the technical challenge and value created from the digital twin technologies. Three use cases are then presented within this presentation. Use case number 1, titled Embedded System, where the system emulates a cooling system with two separate embedded systems set up. Use case number 2, investigate the interaction of frequency modulated continuous wave FMCW sensor system for the wind turbine blade structure inspection. Lastly, use case number 3 demonstrates the runtime interaction with a resilient robotic system, showing all the runtime parameters and information via a single graphical user interface. The presentation is rounded up by highlighting a technical summary and discussion. To provide an overview of our unique digital twin framework, several benefits for engineers have been outlined. Our system can be run on different platforms, such as PC, macOS, Linux, or any edge devices. It can also accept more than 1,000 sensors and actuators in the same section. It also synchronizes data from multiple independent sensors. It provides high-fidelity graphical user interface to represent the runtime situation of assets. The bidirectional communication channels give a chance to the user to preview the upcoming mission before sending the teleoperation commands to the view assets. Also, our framework is ready to be used in any scenarios. So let's talk about the technical challenge. According to our research, we addressed that most of the digital twin models were only designed for the certain use case, which means it is not easy to adapt the framework into other use cases. Data synchronization is another challenge, as it is one of the key elements to enable placing multiple sensors in a workspace and ensure the data describe the same event at the same time. Also, most of the digital twin models do not include the function of bidirectional communication. It causes the physical and the digital world cannot update each others. Data representation is crucial and challenging, as we have to ensure the raw data stream through the internet is meaningful and understandable for the end user. So how do we solve the technical issues? The development of our digital twin framework presents a unique method of data transmission through the internet. By following the system protocol, the system can be protected. Data and commands can be sent using different interfaces. Our framework also synchronizes data without comparing the timestamp of each data stream. Plug and play of sensors and actuators can be performed. It enables both physical and the virtual world to update each other by providing the bidirectional communication channels. From our experiments, we understand that the command should be sent to the physical world as soon as possible. The faster, the better. The color coding and simple graphical user interface were designed for representing the data. One-to-one virtual models with animation were used to reflect the runtime behaviors of the physical assets. Here is the concept of our digital twin framework. To ensure both the physical and the virtual sides are synchronized, there are two communication channels for transmitting data and teleoperation commands between both sides. The proposed framework involves the use of Internet of Things, network communication, communication protocols, data management, and 3D computer-aided design models. This is a non-intrusive method to tune the physical assets as Internet of Things enable devices for communication. Low-cost edge computing devices such as Raspberry Pi could be used as a node of the network communication. A server located between the physical and the digital sides will be a data exchange center to collate, encode, and transmit data at low latency. A graphical user interface program will be given. It is the digital world which allows the user to monitor their assets and plan the mission in the runtime. Before we implemented this framework into the use cases, It was given a connectivity test. Table number 1 here shows that this interoperable digital twin framework can connect and synchronize more than 1,000 sensors and actuators, depending on the platform and the computer resource. It also proves that this framework is stable, extendable, and generic for different platforms, system, and hardware architectures. In use case number 1, we used two independent embedded systems to emulate a small-sized cooling system. This mockup was to replicate a cooling system in a control room with a generator which supports serial port communication. Both the cooling device and the temperature sensor worked independently. Each of them had a Raspberry Pi attached, tuning them to transmit data and receive commands through the internet. The graphical user interface was supposed to display the runtime behaviors such as the temperature reading, the speed of the cooling device, as well as showing the preview of the planned mission. The picture here shows that one of the embedded systems connected to the Raspberry Pi and ready to communicate with the central server. The picture here is the graphical user interface for this use case. It displayed the runtime 3D animation and filtered text information, which demonstrated the concept of simplifying communication with multiple devices using a single interface. It also displayed the runtime rotation speed of the cooling fan with the animation on the virtual twin, in addition to showing the numerical data. The color scheme of the virtual assets help identify with the runtime health status of the physical asset. The digital twin framework acted as a communication bridge, linking two completely independent embedded systems through the internet, and illustrated the runtime information. Operators can preview the speed of the cooling fan before sending the controlling commands to the physical workspace. The preview function was activated when the speed control slider was changed. Another virtual asset showed up for representing the upcoming function based on the speed control slider. Detailed operation commands could be sent to the real asset after the operator agreed and clicked the send button. The goal of the second use case was to display the filtered data graphically from the FMCW radar with no user knowledge required. Human-readable and simple information were the key output. The results of each scan was displayed as a Fourier transform chart as illustrated in the picture. In this case, it required the end users to have a basic background knowledge about the relevant radar theory. In short, the picture here is showing the signal return amplitude in frequency domain for two targets of different materials composition. There is a clear contrast in return signal amplitude from bin 5 onwards. Bin 5 signifies the peak amplitude reflection for target's interface at 10 cm from the antenna. The data beyond bin 5 represents the subsurface internal integrity of the wind turbine blade. However, the operator of this system must be able to understand how to analyze the target-specific data from the generated graphical output and how to map it to the real-world information of the target asset. With using the same digital twin framework, end users could understand the status without the fast Fourier transform chart on the digital twin graphical user interface. A set of color scheme had been designed to reflect the structure of the scan object. This interface also allows users to set the number of FMCW scans and to start the operation remotely. The picture here is the digital twin graphical user interface, and it shows a full-scale wind turbine model, where the blade color was assigned following inspection with the FMCW radar. From this interface, a text box and a button for users to insert the number of times for scanning the objects was provided. These commands were transmitted to the radar system and to initiate the scanning process. In this case, after 10 scans, the system analyzed and returned the result of the wind turbine blade sample. After that, the interface changed the color of the blade on the virtual model. From the end user's perspective, the system provides a single interface to interact with the radar sensor and reveal the analyzed result. This also represents a more user-friendly graphical user interface, displaying a color-coded output that does not require the operator to read complicated 2D fast Fourier transform charts or depend on technical background knowledge. Human-robotic interaction was also investigated for this research. For the last use case of this presentation, a ClearPath Husky A200 robot with two UR5 robotic arms attached was used. Researchers at the Orca Hub has created a self-certification algorithm to monitor the runtime health status of the robot, which enabled the robot to self-certify its system and determine if the robot's able to finish the assigned mission. System ontology messages were communicated to the main system through the Robotic Operating System, ROS, which required operators to have a deep knowledge of Linux operating system and command line interface. Without the digital twin framework, operators were only able to monitor the mission status and the behavior of all components through ROS topic. A graphical user interface was developed to provide a visualized monitor and control panel for the robot. This was a single application to show the filtered information from the ontology messages and to animate the position of both arms. In this use case, an external Raspberry Pi 3 was added and tasked to subscribe ROS topics from the robot. This Raspberry Pi worked as an edge computing device to process the raw data from the ROS topic and communicate with the central server. The use of this additional device ensured that all the computing resources would not be occupied when extra tasks were added to Husky. The graphical user interface of this use case generated the virtual model of Husky in the middle. The virtual model could seamlessly mirror the physical robot. These pictures here are the graphical user interface, showing that it could repeatedly update those parameters from the real robot and use them to change the position of the arms in the virtual environment. Therefore, it proved that the twin and the physical object were successfully synchronized, and the twin could reflect all the runtime behaviors. In addition, the ontology messages were filtered and displayed on the interface as well, such as the battery status, current, voltage, and the temperature of the robot. The top picture shows that the graphical user interface changed the color of the virtual Husky when an error was detected. This sensitive fault warning was displayed via text messages, which could allow the users to acknowledge the current situation for the runtime decision making. The recovery button at the top right corner would immediately terminate the mission, resulting in the return of the Husky robotic system to its base station to initiate further repair actions. Once the recovery button was pressed, the connected Raspberry Pi 3 received a command, which was translated to a ROS topic. The bottom picture shows that this graphical user interface provided a function to control and mission preview for the end user. The user could make use of the Go Twin and the sliders from the graphical user interface to plan the next position of both arms. Each slider controls a joint angle of the corresponding robotic arms. The Go Twins display the upcoming position planned by the users with the sliders. Those commands will be sent to the edge computing device once the user makes the final decision on the upcoming actions, with the behavior of the physical robot driven by the updated plan from the graphical user interface. The implementation of our digital twin framework with those three use cases has demonstrated it is suitable for infrastructure and robots due to the shared requirement for health monitoring. It also provides two communication channels for data and teleoperation commands exchanged between the physical and virtual environment, ensuring both sides are synchronized. The virtual space uses animation to reflect the runtime information on the physical assets and displays multiple colors to reflect transition into different states of health. These use cases have enabled the team at Hello World to better understand the possibilities and applications where the digital twin can aid the area of asset management. From our research, we understand that data-driven asset monitoring is an evolving area of research with advances in sensing technologies. data analytics, and digital technologies. It is vital that to develop a tool to support the integration of information and receiving data from the monitoring systems. We believe that our digital twin framework can improve human-access interaction, requiring less background knowledge from end users. It also offers a direct method to the end user concerned with operational decision support. This framework will be further evaluated in other real-world scenarios for proving that operators can fully interact with their physical assets through the Internet and the virtual workspace. At this point, I would also like to invite you to view the presentation of Dr. Jimmy Branch, who is also a member of the Smart System Group, and he will be presenting runtime analysis of row service condition using non-contact microwave sensing. You can also visit our YouTube channel, Smart System Group, or Orca Hub websites to view our latest research presentations, public outreach, and news features. Here's the biography of the research team. The next slide features the key contact at Orca Hub. Thank you for watching, and we look forward to future engagements.